Hi, I'm Katriana Bruce, and this is my project, Mechanical Loading of a Knee Implant. Okay, so background. So the knee joint is one of the most complex structures of the human body and can withstand significant strain and injury risks in everyday exercises. Normal age-related processes and excessive weight, as well as physical inactivity, can lead to wear and tear of this joint. This project is important because our primary goal is to reduce the pain and improve flexibility. One previous study found that this approach, a knee implant, improved up to 50% in knee motion range. Titanium is the most used material for knee implants. Titanium and titanium alloys have great corrosion resistance, making them an inert biomaterial. A limitation for knee implants is failure of the artificial joint. Joint failure risks increases when one stresses the joint with higher impact activities or a higher weight force. The objective of this study and this project is to develop an understanding of the forces on the knee implant in various exercises such as walking and jumping, and to find the differences in the most effective implant material, and to compare the stresses and the strains that arise from both of these forces and the two materials. So specifically, we'll be analyzing the knee implant with two different material properties, so steel and titanium material, and two different loads, 600 newtons and 900 newtons, to model walking and jumping on a human. Okay, so finite element model details. Here is showing the geometry and finite element mesh. So we can see in the figure, this knee implant has a fixed support at the base, and the top will be a free end. So that is where the joint is, and we'll be able to bend at the knee. Okay, governing equations. So the equations we will be using are from Hooke's law, the general equations for stresses and strains, as you can see. For the boundary conditions, mechanical boundary conditions include a fixed bottoms, like we talked about in the mesh slide, and that is where the tibia and fibula would be attached. And we are going to add a vertical force in the negative y direction at an angle, and this would be applied to model the body weight and the forces while somebody's walking and jumping, going back to the 9,000 newtons and 600 newtons. Material properties. So there are many properties between steel and titanium, but the mechanical and material properties are the ones that we will need to be using. And that includes density, modulus of elasticity, tensile yield strength, elongation at break, and the hardness. Results and discussion 1. So here we have figures 1 and 2 showing the titanium implant with the 600 newton force. So this is modeling a human walking. And on the left, we have the strain contour showing a maximum of 1.7 times 10 to the negative 5 millimeters. And figure 2 is showing a maximum of 1.75 megapascals for the stress. This is showing the model jumping at 9,000 newtons force. And on the left, we have a strain contour of 2.6 times 10 to the negative 4 millimeters, and on the right showing a maximum stress of 25.8 megapascals. Moving on to the other material, the steel implant with the 9,000 newton force. On the left, we have a maximum stress of 25.8 megapascals, and on the right, a maximum strain of 1.5 times 10 to the negative 4 millimeters. And finally, the steel implant with the 600 newton force, a maximum stress of 1.7 megapascals, and a maximum strain of 1.01 times 10 to the negative 5 millimeters. Okay, so here are showing our animations for the 9,000 newton model for the steel material. and I'm going to exit out and we'll be able to watch this on YouTube. So here is showing the strain, elastic strain. You can see here, and the next video will be showing the deformation, the total deformation. Okay, so the summary and recommendations. So our results showed that for the 600 Newton force, the steel implant had a maximum stress of 1.725 megapascals and a maximum strain of 1.02 times 10 to the negative 5 millimeters. The titanium implant had a maximum stress of 1.72 megapascals and a maximum strain of 1.75 times 10 to the negative 5 millimeters. So this concludes that there's not much difference for the stress and the strain between the titanium and mechanical or steel material. And we would need to observe the long-term effects and the wear and tear for these materials. And here are the references.